Hello, everyone, and thank you for attending today's webinar, From Hype to Reality, Accelerating 5G NR for Enhanced Mobile Broadband and Beyond, sponsored by Qualcomm. Before we begin, I wanted to cover a few housekeeping items. On the right-hand side of your screen is the Q&A. If you have any questions during the webcast, you can type your question into the Q&A box and submit your questions to our speakers. All questions will be saved, so if we don't get to answer you, we may follow up via email. At the bottom of your audience console are multiple application widgets you can use. If you have any technical difficulties, please click on the yellow Help widget. Here you can find answers to common questions. A copy of today's slide deck is available for download in the green Resource List widget. Towards the end of today's presentation, we'll ask for your feedback. A survey will pop open on your screen and will only take 1 minute to complete. Your feedback is extremely helpful. An on-demand version of the webcast will be available about 1 day after the event and can be accessed using the same audience link that was sent to you earlier today. I would now like to turn the event over to Heavy Reading's Principal Analyst, Gabriel Brown. Gabe?
Thank you, Stephanie, and hello, everyone. Welcome once again to today's webinar, From Hype to Reality, Accelerating 5G NR for Enhanced Mobile Broadband and Beyond. It's a terrific topic and a very, very timely one. There's been a lot of progress in 5G and in NR, new radio in particular, over the past 6 to 12 months, notably in standards, for example, where the initial study phase was completed late last year and actual standards development is now underway. More recently, in fact, just a few weeks ago, the 3GPP agreed to accelerate 5G NR in what's called non-standalone mode with a view to a freeze by the end of this year as part of its Release 15 work. And so in this webinar, we're going to be looking at progress on NR development, how to accelerate non-standalone mode, and critically, I think, retain a global standard. And of course, we'll also look at some of the use cases and services driving mobile broadband evolution and 5G development. Thank you all very much for joining. We hope you find the session useful and informative. My name is Gabriel Brown. I'm a Principal Analyst with Heavy Reading, where I lead our mobile network coverage. I'm also your moderator for today. I'm joined by 2 expert speakers, both very closely involved in 5G development, and it's terrific to have them both here. They're both open to questions and a terrific resource. So if you do have questions for our speakers, please take advantage of that using the text box on your screen to submit questions. So first of all, I'd like to introduce Lorenzo Casaccia. He's VP Technical Standards at Qualcomm. Welcome, Lorenzo. Could you say a little bit about yourself and what you do for Qualcomm?
Yes, thank you, and nice to meet you, everyone. I joined Qualcomm in year 2000. In fact, as it happens, I joined Qualcomm on the same day as John, the other presenter, for an interesting twist of fate. I've been working in various areas of wireless communication since then, from research to product to policy. And in the last few years, I've been leading our 3GPP standardization team. So I've been directly involved with the evolution of 4G in the latest expansion into unlicensed IoT and similar areas, and then in the shaping or the beginning of 5G. Thank you.
Okay, great stuff. Thanks, Lorenzo. And then we also have Dr. John Smee, Vice President of Engineering at Qualcomm. Welcome, John. Could you similarly say a bit about yourself?
Sure. Thanks, Gabriel. Yeah, so as Lorenzo mentioned, we both joined back in 2000, and since then I've been involved in the research and design and standardization covering both 3G, 4G, as well as Wi-Fi technologies, and then began leading our 5G engineering project several years ago, as we've been really focusing on some of these new innovative techniques and how we can really make 5G NR a step above prior generations.
Okay, great stuff. So let's crack on. I'm going to very quick look at the agenda here. We're going to start with an update on some of the services driving 5G and NR. We'll then look at the technology roadmap for enhanced mobile broadband, really how we can achieve fiber-like performance. That's covering both some LTE Advanced Pro and 5G NR technologies. You might have seen right before this call started, the new gigabit phone was launched in North America. the Samsung S8. And in the third section, we're going to be focused on NR acceleration to provide an update on, as it were, state-of-the-art in terms of prototype systems, and look at some of the trials and demos of that technology. I will finish with Q&A. If there's something that really needs addressing before that, we'll try and work some questions in during the flow of the presentation. But with that, I'd like to hand the call over to Lorenzo from Qualcomm. Please, Lorenzo, the floor is yours.
Thank you. Yeah, we would like to start a bit top-down this presentation. Starting point for us is how do we see 5G into this continued stream of innovation of wireless communication, especially cellular communication, which has been an amazing set of innovation from the earlier generations. Already going from the evolution of 4G to 5G, what we see is cellular as becoming really a backbone or a fabric for connectivity for a large number of activities. So the major trend of communication that we've been witnessing in the last few years is cellular as a pervasive technology that goes from just being a technology for human beings and voice and broadband, but more a connectivity fabric for a number of other activities, whether it's IoT, whether it's automotive, which are two examples in this slide, to many other aspects. And later in the presentation, we will also talk about how cellular continues to expand and enters additional adjacent areas. Broadband remains the driving force for cellular technology, and there is an actual reason for that. Generally, in the natural pace of technology innovation, we see broadband as being the mass technology that drives the innovation cycle of the infrastructure. So because of the innovation cycle of broadband, we see the large-scale investment that bring a new set of technology forward. And then these new set of technologies are then used further and further honed to address additional verticals. So the first phase of 5G, for that reason, will focus on what we call EMBB, which is an acronym that stands for Enhanced Mobile Broadband, and it will address this increased demand for mobile broadband data. We have 3 examples of how this increased mobile broadband data technology curve will, in our opinion, further shape human activities. On one end, we have an additional consumption of content, media, entertainment, or user-generated content, and there's a lot of interesting societal trends that are being fueled by technology that are centered around mobile devices. And this trend of mobile devices being more and more central for content consumption will be further fueled by the additional capabilities that 5G will bring. We have this concept of fiber to the phone, which will, in our view, make it create a real quantum leap in terms of being able to consume content from fixed devices to mobile devices. A second area that we generally like to consider in terms of examples is automotive and transportation in general. So the automotive industry is itself in a transformative phase with, of course, various trends in technology evolution for the powertrain. And as part of this evolution, we see that these transportation devices are becoming more and more computing devices. And a similar trend as mobile phones have now essentially mobile computing devices. We see computing goes together with connectivity. And with connectivity, you have a demand for a connectivity fabric that can support transportation devices. And again, the best connectivity fabric that we have today is cellular technology. So also here, the advent of 5G will create a transformative, will enable a transformative effect also for transportation, for automotive, with a variety of interesting use cases, whether it's enabling autonomous driving, whether it's being able to feed updated information to cars, or whether it's direct exchange of information from car to car for safety or for non-safety scenarios. A third area that is also even more rooted in societal trends, specifically in different parts of, in some areas of the world, is what we see as likely creation of new form factors for devices related to this growing trend for either augmented reality or virtual reality. In general, we can call that as mixed reality. So the superposition of the real world with additional information that again is generated by a mixture of computing, mobility, and communication. So this mixture of mobility, computing, and communication, which of course we welcome and plays very nicely with a number of work that we've been doing in Qualcomm for a number of years, will have as obvious some interesting societal effects, and again will create demands for a different type of communication, high throughput, low latency, high mobility type of communication. So again, we will see cellular communication evolution playing a transformative factor for the creation of these additional use cases, additional device types. So all of these three examples, they go in this same trend that, as I mentioned, they are really the testimony of how cellular communication is becoming more and more fundamental infrastructure for human life in different aspects. Going one step more technical or more concrete, I already mentioned that a general concept that has been guiding our vision on that is the fiber to the phone. So being able, or fiber to the device, being able to provide fiber-like experience to mobile devices. There is a long road that brings us from early cellular communication to fiber to the phone. We have been demoing the concept of gigabit-like communication with LTE already for some time, and as was mentioned earlier, it is also now finally being commercialized. So that is a great step for cellular communication, being able to reach the psychological barrier of gigabit per second communication, which is possible for the first time with our Snapdragon modem family, specifically modem called X16. And that is a stepping stone towards 5G. It gives us a first glimpse of what 5G will bring us if we compare the gigabit barrier to what was possible with cellular communication a few years ago, and then we think that 5G will bring us to multi-gigabit communication. There is a continued roadmap of evolution in cellular, as I mentioned, that brings us from evolved LTE into 5G. How do we reach the gigabit barrier? There is, in this slide here, we try to look a bit under the hood to explain how that is possible. I mentioned earlier on our pioneering work on bringing cellular communication into unlicensed spectrum, which is possible with technology called LAA that has been introduced in technical standards a couple of years ago, and that we have demonstrated already for a few years and have been talking about for a few years. That is a fundamental technology that allows us to put a number of carriers together in the operator network, and together with other fundamental innovation that we pioneered, such as having 4-layer MIMO or high order modulation in cellular modems, allows us to go, as I mentioned, to 1 gigabit per second, and then to have continued roadmap evolution with 1.2 gigabit per second, which will be possible in a next generation modem called X20, and then even further evolution, 1.6 gigabit per second in the so-called category 19 in 3GPP, and there will be more coming soon with a new category to be defined for 2 gigabit per second. These will all be stepping stones towards 5G. This gigabit LTE experience will become a sort of underlying fabric to the introduction of 5G. 5G broadband, as it always is the case for new technology, will be introduced gradually, and there will be a tight coupling between the earlier generation and the new generation from the point of view of the user experience, from the point of view of the cellular operator introduction of the technology, and from the point of view of the network deployments. I'll go a bit more in detail into this tight coupling because the earlier milestone reached by the industry in agreeing into an accelerated schedule for the 5G introduction is heavily relying on this tight coupling. And we can explain that a bit more in a couple of minutes. In this slide here, we also show how also in the area of expanding cellular communication into adjacent areas, there is a thin red line that is connecting LTE advancements and 5G advancements. So LTE has been pioneering a certain set of concepts. Of course, we are talking of a more advanced versions of LTE, not the same LTE that we had introduced about 10 years ago, with expansion into cellular broadcasting, vehicular communication, low latency, support for drones or IoT. All of these, there is therefore a thin red line between the two technologies where all of that expansion that is being pioneered by LTE, and on each of those we could spend some time respect to the specific Qualcomm involvement in guiding the industry for these activities. Those areas will all continue in one form or another in the 5G age. And, of course, 5G will bring additional new areas of expansion for cellular. There is therefore a clear continuity with a continued expansion of capabilities of cellular communication from LTE to 5G, more verticals to be addressed, better capability for mobile broadband, and more spectrum bands to be addressed, which is also another signature characteristic of 5G NR. There's going to be, these are the high-level characteristics, therefore, that have been guiding our work from a 5G perspective. In general, beyond the incremental improvements, and John will go into more detail in those, there's been naturally cycles of improvements in silicon technology or in fundamental concepts that enable 5G NR to take in various areas a certain quantum type leap with respect to LTE. So with 5G NR, we will be able to introduce fundamental lower cost per bit or much higher speed, which will further the fiber to the phone experience. For example, because with NR, we will be able to organically expand cellular communication to new spectrum ranges that were inherently outside the reach of LTE when LTE was introduced. So while on one end there is a red line of continued improvement that goes from LTE to NR, there are of course some areas where there is a clear leap of improvement from NR to LTE, because there are simply said there's being areas of technology were out of reach for LTE and that NR can achieve. It was mentioned earlier that recently there's been a milestone for standards to accelerate 5G, and then we can spend a few minutes on this specifically. Of course, 5G is being 5G NR currently is under standardization phase by 3GPP, which of course is a very high-profile standardization project with large participation. Just a couple of weeks ago, there's been a milestone meeting of 3GPP, of the 3GPP standards, where it was agreed how to structure the overall project plan for the introduction of 5G. And due to an increased appetite in the last year for an earlier introduction of 5G, which has been seen also at Mobile World Congress, for example, it was agreed to agreed to craft the standardization schedule of 5G in such a way to enable earlier commercial deployments in calendar year 2019 compared to earlier plans that were targeting 2020. How is that possible? That is possible by having an earlier completion for the variant of 5G NR called non-standalone. And it is worth explaining what that is or how that is possible. One thing that is worth saying is that this more accelerated schedule was the result of, as always happens in industry standards, of a lot of discussions with interested parties. People, of course, always like to discuss a lot on the tiny details, but eventually it was a very widely shared decision with an incredible amount of industry support, as this slide shows. From technical point of view, it's interesting also here to open a bit under the hood and explain how this acceleration was possible. This acceleration is based on what is called in technical parlance NSA, non-standalone. What does that mean? Non-standalone means that you have an earlier introduction of 5G NR in tight coupling with LTE. You can imagine this as a sort of multi-connectivity where you will have a device that is simultaneously connected to LTE and to 5G NR. This is really a new concept for the introduction of new cellular technologies. There was no such thing going from 1G to 2G, from 2G to 3G, or 3G to 4G. This concept is really building on top of the general concept of aggregating different spectrum bands. It's a concept that's in Qualcomm we've been exploring for over a decade. You can trace it back from the early days of 1xev DO, for those that remember. It's with the multi-carrier DO concept. And then later on, that concept worked its way into LTE with LTE carrier aggregation that allowed aggregation of multiple pieces of spectrum. And if you think about that, it was really, really a fundamental leap for cellular communication. We know that for a variety of historical reasons, spectrum is fragmented worldwide, and also for an individual cellular operator, spectrum is fragmented. Every operator has multiple spectrum holdings that are sitting in different parts of the spectrum range. And carrier aggregation allows to put these different pieces together for an individual user and for an individual device. The same concept also is what has allowed LAA to exist, and therefore also gigabit LTE to exist. And the same fundamental concept that has this lineage of innovation in terms of radio frequency engineering goes now, will bring us 5G earlier, because we will be able to introduce 5G NR in this sort of tight coupling, multi-connectivity setup with LTE, which from bits and bytes perspective will mean that you will be able to continue to use LTE in an initial phase for certain backbone type functions, such as, for example, let's say authentication, billing, charging, these sort of things. And at the same time, you will be able to introduce 5G to have much lower latency, much higher throughput, ability to access large new pieces of spectrum. So really, with this non-standalone architecture, you can get the best of both worlds. You can get the solidity of LTE system, and you can get all the technology innovations that 5G NR is bringing us. So it's really, this is really what allows this so-called 5G acceleration to happen. And as I said, there is a history, a bit of technical history that goes back to about 10, 15 years ago that is bringing us to this important milestone. I wanted to, before concluding, I wanted just to mention that from an industry perspective, and of course from Qualcomm perspective, we are not sitting still on this particular milestone. Already we are thinking of the next phase of innovation for 5G. And in the last 3GPP standards meeting, there's a whole package of new projects that are going to start, that are going to be targeted to a second phase of 5G. And as I've been mentioning a few times earlier, many of them, not all of them, but many of them go in the direction of further expanding the 5G platform to new use cases. So we will, for example, just to mention some, we will have a very important project that will further expand cellular communication using 5G into unlicensed spectrum. Also, that will allow to access large new pieces of spectrum for cellular technology, and it will, over time, allow also the expansion of cellular technology to industrial IoT and private networks. Similarly, we will have an innovation path to harmonize access technologies, which are the ones that we've been talking about here in this presentation, and backhaul technologies, which is always an important factor for real network deployment. As we introduce 5G in higher frequency bands, the cell size is going to shrink, and the density of deployments is going to increase. With the density of deployment increasing, there's a very practical issue that presents itself, which is how to provide backhaul to these smaller cells. And 5G can also be an answer to that. So you can have the same technology to provide access technology and backhaul access. So there's going to be another interesting project. And then a bit more surprising project, but very interesting, and that shows the potential of cellular communication, is trying to reuse 5G technology for satellite communication. We also know from, of course, from the trade news that there is a renewed interest in satellite communication with recent trends on recent improvements in rocket technology. And that will allow to have more satellites being launched. And it's a testament to the capabilities of cellular, that now cellular concepts are also being considered by the satellite industry for their further evolution. And with that, I think having reviewed a very healthy state of cellular technology up to now, I think I can hand over to John to go into even further details.
Thanks very much, Lorenzo. So, it's a great chance to, with the standardization on very firm ground and moving forward aggressively, to kind of quickly cover some of the key technical parts of, what really makes 5G NR different and an improvement over the prior cellular technologies. And so in terms of, what is the new foundation? So one of the points we want to mention is there was this kind of relatively simple approach to some of the prior, generational improvements when we were really moving from, voice communications to enabling, wireless internet in the 2G to 3G transition, and kind of using 4G to really enable, techniques like OFDM and MIMO for kind of wider bandwidth, more multiplexing. And so if we look at 5G, as Lorenzo pointed out, it really is about enhancing the foundation to further support a much wider number of use cases. So as we're designing 5G now and standardizing it, the key point is making sure that we are kind of putting together a very strong foundation such that, even 10 years from now, we'll be talking about 5G evolution just as we're still talking about 4G evolution today. So one of the key points is there isn't really a need to change the OFDM-based waveform. That was one of the, key decisions in 4G that did allow this kind of flexible time frequency grid. And so what we want to do is take that OFDM-based waveform and really expand it into a larger set of opportunities and options in terms of scalable numerology, scalable time in terms of the TTI, looking at optimizing multiple access for different use cases, are really focusing on what are some different things we can do to improve TDD low latency. So making sure that low latency approaches can be commercialized effectively in these new wider bandwidth TDD spectrum, in addition to the lower band FDD spectrum. And the other point is that if we look at all the RFIC and baseband enhancements, basically the Moore's Law type improvements that have occurred in the last 10 years, we want to make sure the 5G air interface can maximally take advantage of all of that technology so that we have really cutting edge processing on the network side, on the device side, in terms of leveraging new bands such as millimeter wave, leveraging much advanced processing like massive MIMO at the cell site, as well as pushing channel coding to the limits, looking at how we can further improve mobility. So it's this aspect of a unified design across spectrum types and bands, even as we still keep kind of pushing OFDM to the limits. So one of the points then is, what are some of these key techniques if we take a step back and that Qualcomm's been working on for many years now, and even prototyping and demonstrating for example, at Mobile World Congress, about 3 weeks ago. And so one of them, as I mentioned, is the scalable OFDM numerology, the ability to cover different bands and bandwidth, keeping a reasonable FFT size. The ability to use this multi-user massive MIMO. So what does that mean on the network side, the device side, and in particular for the air interface, making sure that we put this high frequency sounding capabilities in such that we can leverage the reciprocity. So one of the advantages of some of these key bands being considered for 5G, they're basically around spectrum bands like 3.3 gigahertz up to 4.9 gigahertz. And in that range, the wavelength is smaller, and there's a huge opportunity then to have more active antennas at the base station site. And so making sure that the air interface maximally takes advantage of those approaches. The other thing is we're pushing to multi-gigabit per second data rate. So obviously, as we mentioned, we're already commercializing gigabit LTE today. So as we look to these even higher data rates for 5G, both in the low bands and these higher frequency millimeter wave bands, it's important to have an advanced LDPC code that can really take these wireless performance to the next level in terms of data rate, but at the same time still have that energy efficiency such that the device battery lifetime is very long. And then the other aspect is latency. So approaching latency in 5G with a self-contained TDD subframe enables us to make an air interface that's both forward compatible, enables us to have dynamic downlink, uplink switching, new slot structures that themselves are optimized for low latency, mission critical use cases, and really taking adaptive beamforming into the design from day one. So the ability to steer beams and have this beamforming and beam tracking across the network. So taking these kind of technology aspects, implementing them aggressively on a prototype platform and driving to fast silicon and standardization has always been the way we approach this 5G design. So if we look a little bit at what did we mean by scalable numerology, what we mean is the different types of deployments. 5G is going to be important to have outdoor macro cellular coverage. We want to reuse the base stations that are out there that were deployed, for example, for LTE, leverage those base stations, same infrastructure deployment, same footprint, same backhaul, but add in these new wider band 5G carrier frequencies. And so that's an example where across outdoor small cells, outdoor macro coverage, going to indoor wideband scenarios, and even pushing into millimeter wave. So the ability to take the same approach, but have it be scalable in terms of scaling across these different bands and bandwidths, as well as these different deployment topologies. If we look at channel coding, I mentioned the energy efficiency and the complexity. So one of the key points is how can we do 5 times higher data rate without 5 times higher power? And so part of then is normalizing throughput for a given clock rate. As we're pushing this code rate higher and higher, how can we have then a very efficient channel code that still delivers multi-gigabits per second, but does it in a low latency efficient decoder structure? And so multi-edge LDPC is one of the techniques that was chosen in the Release 14 study item for the high data rate mobile broadband. And that's a great example of what's going to be further defined as we're entering the work item now. So the specific attributes of the LDPC design with hybrid ARQ and fast turnaround. So really pushing the physical layer to the highest possible performance. If we look at 5G NR massive MIMO, so we do have massive MIMO today. It's starting to get deployed on 4G. The point is in 5G really leveraging the fact that it's this TDD spectrum, so time division duplex, where users are transmitting and receiving in the same spectrum. And so because of that, the base station can leverage signals from the user to estimate the channel and turn that around. So that's the reciprocity aspect. So being able to take those cell sites that were deployed in a lower frequency LTE band around 2 gigahertz, for example, and take that same structure and add in a 5G massive MIMO antenna panel and being able to increase the user throughput and the cell edge performance. So being able to drive these 3x, like basically a factor of 3 performance improvement in the user throughput and the coverage data rates that you're experiencing. So one of the key points, in 5G, we do want to enable these new applications. Well, the way to do that is raising the data rate across the cell. Not only that a situation where you get a very high data rate in a situation where you have very good coverage, but also using massive MIMO techniques to improve the coverage and the data rate that users are going to experience across the network. And if we look at millimeter wave, one of the key points is millimeter wave's been there today already for backhaul in many applications. So how can we take millimeter wave and make it mobile? So the ability to have non-line of sight operation, leveraging reflections, having beam switching and beam tracking, and integrating the work that's occurring on the millimeter wave front with what's occurring on LTE and as well as 5G in the sub-6 gigahertz bands, such that you have these efficient mechanisms where if you do enter a scenario where there's not millimeter wave coverage, you quickly fall back with a tight integration with sub-6 gigahertz. So the key point and exciting challenge of 5G millimeter wave is making it mobile, having a robust design that can withstand the challenges of the propagation. There's a huge amount of bandwidth at millimeter wave, and so we really want to bring that into the utilization based on these techniques. So it's an exciting set of technologies that are going to be designed and standardized in Release 15 to enable the millimeter wave operation across a wide variety of mobile use cases, including millimeter wave in a smartphone for 2019. If we look at the self-contained TDD subframe, this is one of the aspects as we're designing for flexibility and a new subframe structure. So one of the key points as we switch a generation is the ability to adjust slightly where are we doing the control information, where are we using headers, how are we enabling dynamic downlink and uplink data. So the key point about TDD is you're switching between downlink and uplink. And so that aspect of designing the system to have that flexible and fast changing between downlink and uplink. So we do need a small guard period, but enabling that switch points to then have the uplink sounding, enabling massive MIMO, driving to low latency with fast turnaround time, and also enabling techniques like integrated access and backhaul, where we want to use the same spectrum not only for access, but also for backhaul. So these are some of the key points that say, how are we looking at the subframe design? And as we look at a lot of the decisions adopted in Release 14, going into Release 15 now, specifically defining these aspects of the subframe. So looking at some of the key points of how do we enable low latency, if you look, for example, at 4G LTE in these different uplink, downlink configurations, well, with a 5 millisecond switch point, you only switch between downlink and uplink every 5 milliseconds, and such that if you have a first transmission and you want to say whether it got through or not, if it was unsuccessful, you're sending the NAC, for example, in this figure here, several slots later, and then only later getting a retransmission. So that latency between the first transmission and the second transmission can be quite large. So being able to decrease that, for example, 8 to 10 millisecond latency down to 1 millisecond by having the faster scalable numerology with these 500 microsecond slots and enabling the fast turnaround and switching. So one of the key points is, yes, 5G is going to higher bandwidth and higher bands, but the real opportunity is also doing things faster in time and having a more compact, efficient transmission that's going to deliver low latency and also compatibility to future systems coming in other time slots. So that's one of the things of the dynamic TDD, where we don't want to presuppose a given uplink, downlink traffic situation. We want to be able to adapt quickly as the user needs change in a given location to have, say, more uplink data to be able to dynamically switch slots such that they can be either uplink or downlink. And so the self-contained TDD design allows for this dynamic uplink and downlink based on the user quickly responding to the downlink control in terms of whether they should be expecting a downlink transmission or actually using the slot to send their own uplink transmission. And so this integrated subframe separates the data and control such that you have the fast switching, and then also you have the downlink control and the uplink control being separated from the data. So this enables a lot of flexible deployment topologies and fast switching. The other thing is massive MIMO. So what are the real approaches? I mentioned this reciprocity. So the ability to use the signal transmitted from the mobile device at the network. And so in this example, if we look at the first integrated subframe where we have the SRS transmitted from the user at the end of that slot, and then the ability for the base station to take that uplink SRS signal, measure it, and decide the pre-coding decision, that is the direction basically for the downlink beam, and use that to send the CSI reference signal, that is the channel state information. So then the base station can then transmit in the next slot the channel state information that's already steered, and the user can then receive that extra channel state information and decide the optimal, most efficient channel quality and data rate that it can support, and then it sends that as CQI feedback. And so then in step 3, you now have the pre-coded with CQI incorporated final scheduling decision. So the ability across time to be occupying the downlink and uplink data portions, but also to really be leveraging quickly the latest channel information such that there's less decorrelation and it's very accurate. And so these are some of the key approaches of what we can do on the massive MIMO side and why massive MIMO and 5G NR can offer improvements over LTE. So if we put these sort of techniques together, then we have this flexible framework with forward compatibility across the scalable numerology, the dynamic TDD, the mission critical transmissions where we have then these short punctured bursts, the self-contained integrated subframe with the fast uplink downlink switching, and then also the dynamic aspect of how is the system provisioning data to the different users and supporting in a forward compatible way different applications, whether it's D2D, whether it's multicast, through the use of blank subcarriers and blank subframes. And so if we look at, we talked a little bit about we're already now progressing from the study item into the work item to actually define the Release 15 specification by the end of 2017 for the non-standalone mode. And so part of the question is, well, why are we ready to do that already? And the answer is that we've been working on this for many years, and we're actually already implementing these, in addition to designing it, implementing them already and having these over-the-air demonstrations, both for sub-6 gigahertz and millimeter wave, as well as we mentioned, taking the approaches from shared spectrum that we've done in 4G and bringing those with a new framework into 5G, new radio shared spectrum, which is also going to be a key study item that's getting addressed in Release 15. So if we look at then these different end-to-end aspects, the part that we've implemented here already at Mobile World Congress, this demonstration of this network-level performance gains with a kind of live user embedded into the network. So this is a live prototype user where it has the 30 kilohertz numerology and a variety of LDBC channel codes, the fast TDD design, the integrated subframe. So taking these implementations onto our prototype platform and doing an end-to-end evaluation of how can we enable citywide coverage in these 5G bands around 3 to 5 gigahertz. So what are the benefits to an overall network operator to deliver that higher performance across the cell and reuse those cell sites that are already out there? So it's one of the key points of how can we bring these new capabilities and efficiency to the sub-6 gigahertz. In addition, on the millimeter wave front, as we mentioned, the exciting challenge is taking a technology that's been used in point-to-point applications and military applications and really look at, well, what are the set of approaches and techniques that enable millimeter wave to work in a mobile, non-line-of-sight operation, so not where you can actually see the transmitter from the receiver and vice versa. And so there you have handoffs, we have mobility testing in a van, a lot of indoor testing and outdoor testing with different handheld users. So the aspect of taking millimeter wave technology and Qualcomm's RFIC and antenna and baseband expertise, getting it into a smartphone form factor, and ensuring the air interface itself has the dynamic algorithms to have that switching and beamforming and beam tracking. So this is going to enable huge amounts of bandwidth to get deployed in 5G across a wide variety of use cases. So this mobilizing millimeter wave has been a very exciting kind of research effort that then evolved into a standardization and product. So it's an exciting reality that 5G millimeter wave is happening in Release 15, and we're fully committed to commercializing it. And so if we look then at the end-to-end aspects, we have these prototype systems and test beds to know that the designs we're carefully evaluating with simulations are also working in field deployments and over-the-air testing and end-to-end implementation. We want to really push the boundaries of silicon for 5G NR. We really do want the 5G NR capabilities to have this new platform that can continue to evolve basically from Release 15 onwards, just as LTE, as Lorenzo pointed out, evolved from Release 8, and now we're already in Release 15 and still improving LTE. It's because it had a very solid foundation. But we want to take all of those lessons we've learned over the years and the latest technologies and enable that new, stronger foundation for the 5G air interface. So take that designs and prototypes through standardization, trials with operators and network vendors, and then drive that into silicon on the modem front and the radio frequency front. So it's an exciting time for us to be really taking 5G end-to-end now and enabling it to show up in consumer devices in 2019. So at this point, we're very happy to answer any questions across the whole range of the presentation.
Okay, fabulous. Thanks very much, John. Good presentation. So we have a bunch of questions coming in. I'm going to start running through them. I'll start with a sort of a more technical one, and please, in the audience, feel free to go as deep as you like with John and Lorenzo. And then we have some sort of higher level, more commercial ones as well. A question is, how is intercell and inter-UE interference mitigated when the TDD subframe performs dynamic downlink, uplink transitions?
Sure, and so that is mitigated by the use of then this gap between the downlink to uplink transmission. So based on the over-the-air propagation delay, ensuring that if a given cell is on downlink and its neighbor is on uplink, that there is that kind of buffer zone such that even within the propagation delay, there is not the interference. So in those pictures, we didn't show all of the different small gaps that are present, but it is that aspect between the downlink to uplink switch that we allocate enough time to handle that over-the-air, microseconds of delay due to propagation. So indeed, that is one of the important parts of dynamic TDD, that in different deployments, you're able to make that fast switch and still mitigate the effect of interference between different transmitters, whether they're users or base stations.
And does that, is it like a diverse downlink and uplink path, is that part of Release 15, or is that a later feature?
Yeah, no, it'll be part of Release 15. That's the part of really pushing TDD to the limit in Release 15 across both the sub-6 gigahertz bands and, of course, the millimeter wave bands. Yeah.
Okay, good stuff. Another question here. I guess I will go to John again in the first instance, but Lorenzo, if you want to contribute, please feel free. Question is the 5G NSA radio, so non-standalone radio, is that a separate physical radio in the E node B in the base station, or does it use using existing RRU? So I guess the question is about what might be a typical kind of cell site implementation of NR in non-standalone mode. Do you have any thoughts?
Sure. I mean, I think the first part, I wanted to make sure if it was a question between non-standalone and standalone, or a question being able to reuse the 4G RF for 5G. One of the points is that on the first element, between non-standalone and standalone, obviously the physical layer is largely common. It's basically going to have the exact same coding, modulation, et cetera. Those things don't depend on network architecture. So that so-called, what we call L1 and L2, is of course common across non-standalone and standalone. which is why the acceleration of the non-standalone really benefits as well the whole ecosystem to also deliver standalone 5G NR, midpoint of 2018 in terms of the standardization. Now, on the radio frequency side, 5G NR will be wider band than LTE, which was a 20 megahertz channelization. We are expecting, for example, 100 megahertz component carriers in some scenarios. And so as part of that, the RF chains for 5G will need to, handle those wider bandwidths. Now, in addition, so we do expect you'll be able to reuse the LTE cell sites as you're writing in the 5G NR radios for the new bands with optimized front ends based on those requirements for 5G NR. So it is something where it's not really reusing the LTE base station other than in the location and a lot of, obviously, the backhaul, the power, and as Lorenzo mentioned, the whole, LTE core network in the NSA mode.
Good stuff. And just a quick follow-up to that. And a lot of, some of the big equipment vendors, obviously I won't ask you to talk about them specifically, but several of them talk about this idea of a 5G-ready base station. Essentially, can operate a 5G NR radio, but essentially on their most recent LTE hardware platforms. Can you just give us a sense of what that's likely to mean in terms of deployment? Is that essentially what you're talking about there? These current platforms, but using a wider band RRU or something like that?
I think this is more related to infrastructure vendors' specific organization of the roadmap. So some of the building blocks have certain similarities from the base station perspective, like handling a certain turnaround between uplink and downlink, again from the base station perspective. So from that point of view, then there are, in the natural upgrade cycles of 4G, because you can try already to introduce in your roadmap certain aspects that then carry similarities with 5G. That has more to do with the baseband roadmap of infrastructure vendors. But like John said, then there are natural differences from the RF perspective. So I think some of the terminology, because some of the terminology is rooted in natural technological progression, and some of the terminology has to be taken a bit with a grain of salt, in a sense.
Sure. I can stick with you then, Lorenzo. There's a few questions around this topic, and John, contribute as you feel appropriate. Next question. Is NSA radio in 3GPP Release 15 going to combine existing LTE bands with new 5G bands? And I'll just add a second question onto that, so it's quite a similar one. How will vendors and operators deal with the existence of multiple RAP technologies at the same time, so 2G, 3G, 4G, 5G? Lorenzo, if you could take sort of kind of bundle two questions together there.
Yeah, sure. Yes, of course, this NSA will combine LTE bands, some LTE bands with new bands. As always, spectrum is like oil fields for the oil industry, so it's really the backbone of the industry. Spectrum, unfortunately, tends to be fragmented, so there are different spectrum ranges of interest worldwide. However, there's an emerging consensus around certain areas of the spectrum range for the introduction of 5G. So we see a lot of interest around the 28 gigahertz range, 39 gigahertz range, 3.5 gigahertz range, and maybe 4.5 gigahertz range, and to some extent also 700. So these are the spectrum ranges where we anticipate earlier introduction of 5G NR, and all those, of course, each of them in their own region, and they will be combined with the spectrum holdings that the operators have where they have deployed LTE. As there will be also there a certain set of band combinations, in the same way as we had band combinations for carrier aggregation when we had carrier aggregation in LTE, and we continue to have it. We will have bandwidth combinations between LTE and NR. Then you ask very valid question: how does 2G, 3G, 4G, 5G coexist for the operator? Naturally, there will be some level of refarming over time. I think we already have seen some operators somewhere sunsetting 2G networks, and this phenomenon of sunsetting either 2G networks or 3G networks will occur in different regions for different operators at a different pace. For example, 2G networks are in very highly valuable spectrum in 900 megahertz. So there is interest to reuse that spectrum for certain operators to introduce newer technologies. So there will be a natural phenomenon of rationalization of operators' networks from the radio access point of view. That's for sure. It will also be made easier by this other technology trend that is relates more to our friends on the infrastructure side. We are all aware that there is this trend of multi-radio base stations, so newer equipment from infrastructure vendor is capable to handle multiple technologies simultaneously. In a certain sense, also enables transition in the industry towards more LTE and NR over time.
Good stuff, thanks. Okay, another question now. I guess I'll go to John, but Lorenzo equally, if you wish. Will operators deploy both NSA non-standalone mode and standalone 5G NR, or will it be one or the other? Perhaps, John, I could go to you for that one.
Sure. I mean, I think you'll see many operators want to get the long-term benefit of the new core network, the NGC, which is obviously differentiated from the LTE EPC. So NSA is a great way to enable a fast, aggressive rollout that leverages the LTE functionality that's already there and is not required in terms of delivering a 5G radio experience from the cell site to the user as soon as possible. So it is something where NSA is a great way to get going quickly. Long term, an NSA deployment allows you to continue to upgrade to SA. So the ability to reach the standalone 5G optimized core network as well. So you'll see different operators take different approaches, of course, but the end game of eventually enabling a new 5G core network is part of enabling these larger number of use cases, network slicing, virtualization, etc. So the core network is also going to have a significant upgrade path that can be phased and staged the same way that, there's not going to be instantaneous nationwide coverage on the radio side either. So it does allow a smooth addition as 5G's additive into a 4G network.
If I can also add something, if I may also add something, we mentioned in passing this continued expansion of cellular technology, and then we see 5G also to become important technology for additional use cases that not necessarily will go through traditional operator deployments. So, for example, we will see, we believe, cellular technologies being used more and more for private deployments, private networks, industrial IoT. This also relates to all the work that we have done in Qualcomm with unlicensed spectrum. So all of these type of deployment in specific niches, let's call it that way, even though those niches can become very substantial, they will naturally require a standalone architecture because they will be kind of self-standing deployments that are that will be put in place by new actors and for specific use cases that were not possible earlier with previous generation of cellular technology. So the continued evolution of cellular into additional niches will naturally bring more demand for this standalone architecture. That's why we never saw the two as competing with each other.
Yeah. Okay, good stuff. Okay, thanks both gentlemen. We've come to the top of the hour now, so I'm going to wrap up the session. Thanks to everybody who submitted questions. There's a fair few we didn't get to, so I'll ask the team here to review and, if appropriate, respond by email. So it remains for me to thank Lorenzo and John from Qualcomm for today's session. Very informative. Thank you, gentlemen.
You're welcome.
You're welcome.
And last but not least, thanks to everybody in the audience for attending today. Thank you all very much, and goodbye.
Bye-bye.
Goodbye.